So we talked about stability a bit this morning. The topic is not going to come back until we start talking about specifically the subject of atomization. So, and that's going to be, I think, on Friday specifically. So at this point, what we're going to be discussing in more details is the specifics of interface tracking method. So we discussed earlier this morning about, I guess I titled this liquid gas flows / interfaces in CFD. We're going to get to the interfaces in CFD part of things. We will reconnect those interfaces to liquid gas flows, but we can be to some extent agnostic regarding how the interface is going to be used. And again, by interface, I mean surface, 2D surfaces in a 3D domain, or 1D surface in a, or 1D line in a 2D domain. So we're going to be identifying the location of objects like that. The usefulness, like I've been suggesting, transcends the question of multiphase flows. For example, if you're interested in the topic of combustion, and if you're interested in simulating premixed combustion, so situations wherein a combustible mixture ignites at some point and burns at a certain, where the flame front moves into the unburned gases at a certain velocity, well, in a situation like that, it might make a lot of sense to track the location of the flame front. And one of the ways you would do that, potentially, is with an interface tracking algorithm like we're going to be discussing. In particular, today's algorithm, level set algorithm, has been used extensively by people doing simulations of premixed combustion. So that's another example. There's others. Probably the third most common use of level set type techniques or similar surface tracking type of techniques is something we've talked about last week, which is immerse boundary methods. So if you're in a situation where your object has a complex shape, and so you have a solid object of a complex shape, and you're interested in the flow around it, and you're not, you would prefer to stay away from methods that mesh accurately the surface of that object. Well, one approach is to acknowledge that your mesh, imagine this underlying grid here is your mesh. If your object has this shape, you can still represent it through some sort of, by modeling essentially the effect that each of those boundaries has on the grid cell. But first and foremost, you need to know where this interface is located. So if the object you're trying to represent is a sphere, like we were talking about last week, that's not particularly difficult. You track the centroid position, you know the diameter, you're done. You know exactly where the object is. If the object looks like this with potato here, the story is more complicated. You don't know a priori. Knowing the centroid is not enough to know exactly where the edge of the object is located. And so to deal with something like this, you would need to use some sort of a level set technique or a technique of the same type. Another use that now transcends CFD is medical imaging. If you want to identify features that are observed when you perform, when you do CAT scans, for example, you might observe objects that, or at least shadows on your medical image that could or could not be problematic depending on their geometric characteristics. So if you're a doctor analyzing those images, one thing that you might be interested in is placing a contour around the region, maybe the darker region that signifies maybe a denser mass of cells. That could potentially be problematic, maybe tumorous in nature. And one way of doing that is to track an interface and have it move towards the object that you visualize in your image in some way, such that you ultimately obtain a mathematical representation of your object that you can then analyze quantitatively. So that's another use of, in particular, level set techniques. Okay, so the topic today is going to be level set methods. This will be pretty introductory, and we'll talk about a few different ideas. First, we'll introduce what is probably the most naive way one might think of tracking a surface, and we'll show some of the limitations of this naive way. And so we'll argue for the need for something better, or maybe more flexible at least. And we'll introduce this concept. I'll show you concretely for the first, we'll look a bit at the code, and I'll show you how to set up this type of interface tracking for a concrete problem. And then we'll go through the discretization that I put in the code. We'll explain why I used what I'm using, and we'll give some reasoning behind this. And so then we'll look at the code, we'll run a simulation, and we'll move to a second test afterwards. Let me give you first two key references. I think one of them is in your course pack. Oh, and I should say the course pack for today contains quite a bit of information, general information on level set methods. We're not going to follow that. We'll go back to it tomorrow and the day after tomorrow. We'll just go pen and paper today. So the first paper that I'd like to point you to is by Mark Sussman. Smerica. The lead author, I guess the PI for the work was Stanley Osher, an applied mathematician. The title is A Level Set Method for Computing solutions to incompressible two-phase flow. This is a journal of computational physics paper, and I have the full reference, so I might as well write it. Page 146, and it's from '94. So that's the first reference. The second reference is also from Osher's group, and the collaboration with a few other people. It's Peng Di, Merriman, B, Stanley Osher, Zhao H, and Kang M. This is a PDE-based fast, local, level set method. The paper is again a Journal of Computational Physics paper. Uh, 155, page 410 from 1999. The second paper is probably considered to be the standard, state-of-the-art, well, I should say the state-of-the-art implementation of the standard classical level set method. Okay, we're not going to do that exactly because we can allow ourselves to take a few shortcuts for our purpose here. But we'll have the same ideas in what we're going to implement. Okay, so those two references, if you're interested in level sets, I would suggest that you take a look at that. Okay, so the first topic we're going to start by discussing is the question of if you were to start completely from scratch, and if you were tasked to follow a surface or in 2D follow a line, what would you do? Well, probably the most natural way would be to put points along the surface and follow those points. Okay, so we'll talk a bit about what that approach entails. So we'll talk about the marker approach for interfaces. Yes? Oh, okay. Yeah, go ahead if you can. Is it better? Okay, so we have a grid. We're doing CFD, right? So we have a grid of some sort. And that grid, on that grid, we want to keep track and represent an interface that might look like this. This will be our X. And this will be our Y. Is it better overall if I write more bold? Does it help or does it not matter? Okay. So, one question you might be interested in, the first question you need to consider is what do we need to know about this interface? So ultimately, we need to know information about a number of things. We need to know about what fluid is on each side of that interface. That's specifically something that the flow solver needs. And as a consequence to that, the properties of the flow on each side. So density, viscosity. Right, that's not a particularly complicated statement. The other important aspect is the location of it, right? So this is the other important piece of information. So we need to be able to relate the interface to which fluid we have, and we need to be able to say something about where the interface is located. We can add a few more things. If we want to implement a flow problem where surface tension plays a role, we're going to need to be able to calculate the curvature of that interface. The list continues. If we were looking at a different problem, say for example, if we were looking at a premixed combustion problem, and if this interface was tracking a flame front, we would want to know something about the flame thickness. We would want to know something about the local temperature. We would need to know various pieces of information that are tied to this interface. So potentially we would have more surface information. For example, some interface thickness that might be relevant if your interface is actually a flame front. In a liquid gas flow situation, that thickness from looking at the microscale physics is going to be very, very small, on the order of a few tens of angstroms. If we're doing CFD, we probably don't care about that. So in our case, by our case, I mean really for liquid gas, multiphase flows, so if you're looking at liquid gas flow, you'll let that thickness go to 0 and consider the flow to be discontinuous. Okay, so the thickness going to 0 means that we simplify our life a bit. We don't have to keep track of that, but we're going to be facing discontinuities. There's one more piece of information that we need, which is what is the equation that controls the transport of this interface. So the main thing we're going to focus on at this point is going to be the location and what governs the transport. We're going to build those tools today, and we'll add more to that. We'll talk about curvature in the next few days, and we'll talk about how to use information from the interface to tell the flow solver which side of the interface we're on, and so we'll do more of that as we move forward. Okay, so probably the most naive way you can think about this interface at first is to say, well, if you sketch it like that, this is an interface height as a function of x. That, something like that could be solved. We could recast this problem as a 1D problem. So how to describe the location? You can say this is a y interface, which is equal to a function of an x position. It should be clear that in the sketch here that works, right? We could have in each cell information about, we could store an additional array which is a height as a function of x. But in the general sense, this doesn't work because our interface might look well, this is not the best sketch. Let me redo the sketch. Okay, so if I sketch it like that, it becomes pretty obvious that my height is multi-valued here. I don't know how to define my interface using this simple relation if I have multiple interfaces at each x location. And you might say, well, then do it in store an x location as a function of y, but then I'll just respond to you that what if my interface does that? Okay? So this is not a viable option. We need something better. The something better that we're going to look at is some sort of a parametrization of x of y of the interface written as a function of time. Okay, that's going to be probably the next logical step. If I place a marker, some sort of a Lagrangian piece of information that I tie to the interface, and I follow its position, then I will know something about the position of the interface. So that now would work, even for this very ridiculous shape that I sketched. If I were to distribute markers, so if I were to create a collection of positions like this, I would be able to represent that interface. So let me, in fact, I'm getting ahead of myself a little bit here. Instead of writing this as a function of time, let's say that we right now just simply introduce a parameterization of our surface as a continuous x of y as a function, x and y as a function of some parameterization s. Okay, so this is a pure surface parameterization. And then this is fine, but this is continuous. We're going to go discrete. If I discretize that, what I end up with is a collection of points at the surface. Which are those green dots that I showed above, which are characterized by an x sub I and y sub I. Okay? So now I have lots of particles. The parameterization suggests that they have an order. So we have to be careful here. This is ordered, and that will give us problems. And we're going to call that marker points, marker particles, surface markers, call that anything you want. Okay, so we have a surface, we propose a parameterization of it, we discretize that parameterization. Now a surface is a collection of ordered points. The fact that we're proposing an order implies a certain connectivity. A point comes after another point, meaning that if you're sitting somewhere at a point xi, yi, you have a closest point to the left, a closest point to the right. You can find your neighbors. So that's something that needs to be included in that. Order implies connectivity. Connectivity, in some sense, we won't go very explicitly there. So those points, this is not a cloud of points, there's some knowledge about which point comes first. And so now if we want to represent the interface, and if you have some sort of connectivity between your points, you can simply draw a line between your neighboring points. Okay, it's especially obvious in 3D, in 2D. In 3D, now you have to place planes, but you just have to connect points with a line to obtain an approximation of the interface. Which we can do right here. In this case, our corresponding approximation would look like this. All right. So that's an easy enough concept to use. There's nothing particularly difficult. If I tell you represent a circle, you'll distribute points along the circle, and you know, this is the end of the story. You can easily create this. Now the question is, how do you move the interface with that representation? Which is the second point here, what governs transport. So now that we know the location, how to move the interface. Well, the good news for us is that this interface we're assuming, at this point we're only doing kinematics. We're tracking a surface. So we assume that we know the velocity it is given to us in some way. We'll be solving for it very soon. But if you know the velocity and the surface is a material surface, then you know that those points are just moving at the velocity that is prescribed. That's exactly what we've been doing last week. This is Lagrangian point tracking. There's nothing difficult here. We'll be solving d sub xi, where x is now an array, over dt is equal to my local velocity evaluated at position x sub I. So this is assumed, this v is assumed to be known. And this v at x sub I, well, we'll have to obtain it via an interpolation that might be the same bilinear interpolation that we did in the previous week. So it's obtained by interpolation from a CFD mesh. This, we've talked about how to solve that. We're not going to spend any more time. You can use Runge-Kutta techniques or anything like this. Okay. Why are we not going to do that? We're not going to do that because this method ends up, it looks like the most simple, the most obvious method that you would use to represent a surface. It ends up being a viable method, but also one of the most complex that you can deploy for actual simulations. Okay, so it exists. I'm not going to say it doesn't exist. We'll talk about it in more, yes, we'll talk about it in, I think, more details tomorrow morning or the day after. So it exists, but it is complex for many reasons. There's two particular simple examples that we can look at. One problem is, imagine, even still sticking to 2D, what if my collection of points gets curved like this, in a flow that forces those points to move downwards and those points to move upwards? Well, after a while, this will be a solution, or something like this. And that's problematic for a number of reasons. So it's obviously problematic because if we have an incompressible flow, trajectories that are tied to the flow, pure material trajectories cannot cross. And it's also problematic because our connectivity is going to become all bogus here. It's going to be very complicated to have a clean connectivity in a case where we've created a loop. In a general sense, any situation like this where two interfaces are getting pushed towards one another, it's going to be very difficult for us to distinguish between well, I'll stop sketching the points, but it's going to be very difficult to differentiate between this or maybe this, or maybe, okay, I don't know where this came from, or maybe this. So as soon as we start to bring our connectivities, our points towards one another, it becomes very, very difficult for us to distinguish between a point that comes from a different interface from a point that comes from our own interface. And if our interface is supposed to actually change topology, then we need to actively be able to say, well, point I that was part of this interface that came from the right is now going to belong to this interface that moves up. Okay, so any type of topology change, so this is essentially a statement about topology changes are an enormous challenge. And so stemming from this observation, that it's very difficult for us to deal with those reconnections and overlapping points, comes a second the second problem, which is that if you actually design a method that has the capability of dealing with those situations, it is a very involved and complex method. All right, so let's treat that as an intro to the problem. The naive approach ends up being viable, but with a really high entry, really high cost of entry for development. So we'll take a different direction, okay? This direction will be based on the so-called level set approach. So how did I do this? I did, so let me write this as part one. This way we can say part two level set definition. So we'll continue with level sets tomorrow. So we're not going to tell the entire story of level sets right away. But yes. So the level set idea is a very interesting idea. Instead of keeping track of points at the surface, we're going to keep track of, if you will, a topographical map on our mesh. So we're going to have information that will be that will more rich than simply the information of the interface location. So we're going to do something like this. Imagine you're looking at a map. And what we're going to say is that we have some interface. And from the perspective of looking at, again, at the topographical representation of the problem, imagine if you had a map, it might tell you that on that side you have, say, water, an ocean, and on that side, not red, green, on that side, say you have land. So that's the representation we're going to follow, because this representation that gives us those two different colors for our entire map is sufficient, in fact, to tell us where the interface between those two colors is located. So if we want to find the interface between in our example, if we want the interface between water and land, it's simple. The only thing you have to do is take the 0 meter isocontour of a height map. Or not height, I think you would refer to of an altitude. Map. Right, so that will tell you directly what is the, where is the interface. So if the altitude of the ground, say you call it phi, if it is less than 0 meter, you're dealing with water. The ground is underwater. If phi is higher than 0 meter, you're dealing with land. We're going to use exactly this strategy in order to distinguish between liquid and gas. Okay, so we'll have an altitude, an auxiliary altitude map that will tell us which side, which phase we're on. So concretely here with our altitude phi, anywhere where phi is equal to 0, that's the location of the interface. Okay, so let's translate that to our problem of liquid gas flows. If I have y and x, say I'm interested in looking at a bubble, then, well, it would probably be closed, so let me try again. Whoop, good enough. So this is going to be our liquid gas interface. Inside we're going to have a gas. And we're going to use the same definition, which is that our phi is going to be here. Well, is it, well, we need some definition, so we'll say phi is less than 0. And outside, we'll have our liquid. that will correspond to phi greater than 0. Okay? Same exact strategy. Now, what we're going to keep track of is going to be this phi quantity of x and y and time. Okay? And from that, the definition of our interface will be, so we track that, and you can define the interface. Let's call this interface gamma. Define the interface gamma, that's a weird gamma, by the fact that phi of x gamma, y gamma, and t is equal to 0. All right? So we're not explicitly finding those points anymore. We're not keeping track of a collection of x, y at the gamma interface. Instead, we're going to ask ourselves, what is this altitude map, so from which we're going to be able to re-extract the interface. The interface here is just the 0 iso contour, or the 0 iso level, or if you will, the 0 level set of this function phi. Okay? Hence the term level set method. Now, so for a level set method, we introduce a function that, by the way, we call so-called a level set function. Phi, such that gamma is equal to the ensemble of points in our general space, such that phi at that location and at that time is equal to 0. Okay? That's our definition of, this is going to be our strategy here. Does that make sense to everyone? This is not a particularly complicated concept. If you've seen it before, it's an obvious thing, but it's also something that's easy to miss the first time you look at it. And I wouldn't want to spend 2 days talking about something that doesn't sink in. Okay, any questions on that, or is that obvious to everyone? Why I can introduce a function of x, y, and t, and from that define an interface as an isosurface? Okay, everyone's good. So now the question is, what is the equation that I should solve if I want to figure out what my phi function is? Well, that's a more tricky question. We knew definitely what is the equation that controlled those points x sub I, y sub I at the interface. This was easy. This was pure material transport. Well, now we're saying that we're assigning at those points a value, essentially, right? We had, in the first method, the marker method, we had points x sub I, y sub I. And they were undergoing material transport. Now we're saying that those points also have the additional information that their corresponding value of the phi function is 0. Well, but those points still obey material transport. So what we know is that our function also obeys material transport at those points. Make sense? We've tied a level set function to those points. We've said at those points x sub I, y sub I that just obey material transport, that just are materially advected by the flow. We're saying that the value phi is 0. Okay? That means that if I move my point at the velocity v, that point carries along with itself its value of phi is equal to 0. Okay? So as a result, this is my equation for my interface, which means that I need to solve d phi dt plus, if I stick to my v velocity, v dot grad phi. All this, let me put a normal bracket, all this taken at the interface is equal to 0. This is my correct equation. Outside of those points, I have nothing to say on this function. I've given myself no possible information at this point. However, it pays to be pragmatic. So if this is the equation we want to solve at gamma, one way of achieving that is by solving this equation everywhere in our computational domain. This way we know that at least at gamma we'll be solving the correct equation. So we'll generalize that to the so-called level set equation, which is nothing particularly exciting. It's just pure material transport of our phi function. So this is the equation we're going to be solving. A simple material advection problem at the fluid velocity. So now we need to add more information to this, or else we're going to be a little bit stuck. So we haven't defined anything except the fact that phi is 0 at the points of interest. That means that at this point, our phi function as a function of some x can be pretty much anything it wants. From our definition so far, we know that, so if I have gas here and I have liquid here and I have gamma here, what have we said so far? We've said that our function needs to be 0 right at that location. And then we said that it needs to be positive in the liquid and it needs to be negative in the gas. So that's an acceptable level set function for us to use. This is a completely acceptable treatment. So here, phi is equal to 0. Here, phi of phi is larger than 0, and here phi is less than 0. That's all we've given ourselves. Transporting this function is somewhat complicated. We need schemes that have the capability of dealing with all those little wiggles. One way to make our life easier, and we'll get back to that tomorrow, it would be ideal for us if this function was absolutely smooth. It is easier for us to transport a perfectly linear function than it is to transport a weird-looking function like this. So this is an acceptable choice of phi, but this right here would be an ideal phi for us. Okay? Smooth, it is smooth. No local extrema. At least as much as possible, which will make the transport more accurate. So the way we're going to do this is by introducing the concept of a distance function. So we'll say, well, if our goal is to have a function as smooth as possible, one way of achieving that is of having a constant gradient of that function. So we're going to say again, ideally, the best choice is grad phi. So we're going to work in 3D, so we need this to be a magnitude. We'd want to take this to be more or less equal to 1. If you take this to be, so in particular, if grad phi is strictly speaking equal to 1, then you're working with what's called a distance level set, a level set function. Why? Because magnitude of grad phi is equal to 1 means that you have a unity slope. So if you move a distance x away from the interface, then the value of your phi is going to be x. So that means that the value of the level set itself will be the distance between you and the closest point on the interface. So it tells you something about your distance from the interface. Okay, so I said no local extrema. When I wrote that, I meant we got rid of these local extrema in this weird sketch I made of a random function. We haven't necessarily completely removed the existence of local extrema. And this you can think of by going back to this bubble here. So if we were to sketch, let's say, let us sketch what the distance function looks like, or what your distance level set would look like here. It would be positive here, negative here, 0 all around, and at every point, you would just essentially have the distance from the point on the interface. So if you plot it along this central line, so example, middle of our bubble, this is our phi. This is our x. Our interface is located here and there. Those are the two sides of our bubble. The middle, how did I write this? I used black, and so this is our gas, in which phi is less than 0. And this is our water with phi larger than 0, and our water with phi larger than 0. So now our function will look like this. Oh, did I do it the other way around? Yes. What am I doing? There you go. So this will be your phi function. And so one of the topics for us that we won't be able to avoid will be the discussion of this corner here. This function, it is practical as long as you're in the situation where you're dealing with a single interface. As soon as an interface gets close to another interface, so in most situations where the flow becomes a little bit more complicated and the interface folds over itself in some way, you end up with local extrema and minima, which according to our definition, if we want indeed to have a near constant gradient, those will become problematic. And so from the perspective of transport, we'll have to be careful about this. Okay, we can sketch this in 3D as well. So here, so this is here, I said distance function, I should have added one thing. Let me add one important word here. Before the distance level set, this is a signed distance level set, okay, which change sign based on which side of the interface we are. Okay, we'll do one sketch that will probably look, that might not look very good, but I'll try anyway. So for our true bubble in 3D, this is our phi. This is our y. And this is our x. Our bubble, that's ugly. That's okay. So this is our bubble that we sketch above, okay? In xy, we have this bubble sitting, it's spherical. Now, distance level set, in that context, will look like this. So in here, phi is less than 0. Up here, phi is more than 0. Along here, this phi is equal to 0. So in red, we're really visualizing here our phi is equal to 0 as a surface. Okay, so this is really, a bubble is a conical shaped object if you look at it in phi x, y space. Okay, makes sense? Well, on the same page. So the equation, I'll just rewrite here one thing. If the divergence of the velocity is equal to 0, then we can equally solve d phi dt plus divergence of phi v, or d phi dt plus v dot grad phi is equal to 0. Both are equally acceptable provided that the velocity field is solenoidal. If the velocity field is not solenoidal, the conservative form is not the correct form. It is the non-conservative form that is the correct form. We're doing material transport, we're not conserving phi. Any questions? Everyone's clear with what we're using? Okay, so now we're going to run one specific case. But before we do that, we're going to talk about, so there's two more things I want to talk about. First, how do we set up a level set flow problem? I shouldn't say flow. How do we set up a level set problem? So we'll talk about the initialization of the level set, which is a tedious exercise, but not a complicated exercise, but I want to mention it for things to be demystified. And then we'll talk about the implementation of of that equation specifically. We'll do a first version of that. We'll talk about it some more tomorrow when we'll solve a different version or a different equation. So this was our part 2 here. Now we're going to do part 3. Initialization of a level set field. So we said exactly already what the level set is. The level set can be taken as being the distance from the closest point on the interface. So we're going to make use of this. The first problem we're going to look at, and the only one for which we're going to talk about the initialization, is the so-called Zalizak disk problem. So Zalizak was a pretty prolific numerics researcher who published quite a bit on flux correction algorithms. The idea was to avoid numerical diffusion as much as possible. And so he was looking in general at scalar transport with the idea of minimizing numerical diffusion. That was his goal. And so he created a nifty little test case that somehow, for some reason, I don't actually know the history of that, has been picked up by the multiphase flow and interface tracking community as the de facto reference case that everyone starts with. And so we're going to start with that. It's not a particularly, well, it has some good things and some bad things. So we'll take a look soon. But the idea is that we're going to be looking at the solid body rotation. So we're going to impose a linear velocity field. So we're going to do solid body rotation. The idea is, well, we could do a circle, but a circle is too easy to represent, and it's too easy to transport right. So what Zalizak did is he dug out a little notch in this circle, making it a very complicated shape. So we're going to do a solid body rotation of a notched disk. So this is how this is going to look. We're going to give ourselves a square domain. And in that, we're going to create it started so well. And assume it's a good-looking circle. There you go. We're going to create a shape like this. And then we're going to make it rotate under solid body rotation. That means our velocity field is going to be given by minus y plus x. We'll normalize that to include the 2 pi to allow us to integrate for 1 time unit. We're going to do 1 rotation, meaning that this thing should just go back. If we had a perfect transport scheme, this thing would go back exactly to its original location. So after 1 period, or I should say exact solution is equal or is the same as the initial solution. So we'll have a few parameters. One parameter will be the radius of this circle. We'll have the size of the notch, so the width and the height of the notch. And then that's it. And the location of the center of the object as well. So let me go. So make sense to everyone what we're doing here? Now let's look at the code. We were here already. Let's look at the code for a second. So in order to not flip back and forth, I'm going to be directly showing you the code. If I can find it. There you go. So this ugly block of code is the initialization of this thing. This is, like I said, pretty ugly. So I'm not going to go through the details, but I'll show you how you get to that. There's nothing mystical. It's pretty straightforward, but it's pretty annoying. So let me resketch this thing in a little bit of zoomed in. This is the worst circle I've ever done. Yeah, it's not very good either. Okay, let me see. Plus figure, there we go. That doesn't help me, I still make potatoes. Okay, well. Now I have a potato, all right. Okay, never mind. We'll go back to our attempt at making potatoes. Okay, we try to be precise enough to have something interesting to talk about. So we're going to distinguish between different zones here. I'll do that using my thin color, my thinner pencil here. We'll put phi less to 0 outside. How do you compute in this entire outside region this phi function? Well, it's simply going to measure the distance from the circle. So right here, you put a negative sign, you measure the distance to the z-exact circle, and you're in business. So that takes care of this entire distance field. Careful down there. My circle has been cut out, and so right here I'm not going to measure the distance to the circle. The closest point on the interface, if I'm sitting here, say, will be that corner point. So I'll need to carefully keep track of what my geometry looks like and make sure that right here I measure my distance from the corner point that I might as well name. So let me call that point C1, and that's going to be point C2. Okay, so along those regions, I'm going to measure my distance from those corner points. Everywhere else, I only care about the distance from the center as long as I'm outside. From the circle as long as I'm outside. So this is distance to C1, distance to C2. You can see already to generate the distance field outside, we have 3 if statements. As we go back, as we go up inside the notch, the story continues, although it changes a bit. Because as soon as I move above the line here that separates C1 and C2, or that links C1 and C2, suddenly my distance changes. It might be the distance to C1 or the distance to that plane. No, what am I saying? No, this is necessarily the distance to that line here. Line. So, sorry. So right here, I'm looking at, so let me give a name to this line. If this is line 1 and this is line 2, here I need to provide the distance to line 1 and here the distance to line 2. Okay, so a few more if statements. I left out this little corner region here because starting at 45 degrees from that point and 45 degrees from that point, my distance suddenly becomes closest from that top line. So I have to involve line 3 here. That is the same color. For this top little wedge thing. Okay, now you can see where we're going with this. As I continue this time inside my circle, I have this blue region here. So now we're getting to the phi larger than 0. Those points will be defined by taking the minimum between that distance, or the distance to that point and the distance to that lane. So any point here you'd have to try to project here or project here, and you would take the minimum distance. So this would be the minimum of distance to circle, comma, distance to line 2, and here the minimum of distance to circle, comma, distance to line 1. And for the sake of completeness, we'll add this top region here, right above that line. Now we're going to have to take the minimum between the distance to the circle and this time the distance to line 3. And we're left with these two that I won't color, where now you'll have to look at the minimum between the distance to the circle to the corner point, and the minimum of the distance to the corner point. So this is going to be min of distance from circle, comma, that point I'm going to call C3, and that point I'm going to call C4, so that's going to be min of circle, comma, C4. There we go. Okay. So there's nothing particularly complicated, but it is tedious. In general, initializing distance fields is tedious. Every type of angle in the object shape will lead to messy little things like this. So what I'm doing in the code. So first of all, this is the single phase code. We don't have any particles. I removed all this for simplicity. We're starting from the base code from Monday, last week. There are two entry points in the code, in the main demo flow F90 code. One is a level set underscore init call, early before the time integration, like we did for LPT init. The second is a call LPT underscore step, and that's within the time integration loop. What I have in this code as well is for today and I think tomorrow as well, and maybe also the day after tomorrow, the flow solver is commented out. Okay, so we're just basically time integrating the level set equation. Since here we're going to provide solid body rotation velocity field, we don't need to solve for it. I'm outputting the level set, and at this point only the level set. So this field, this phi field is the only thing I'm outputting. One thing as well, in the code I didn't call it phi, I called it G. G is the kind of standard name that's been used for a good number of years for combustion, for premix combustion level sets. It's been classical to call that function the G function. All right, so that's our initialization. Let me show you so I think I showed you this already. So this is where I'm doing all this. So that explains all those if statements. So we're not going to go through that. There's no science in here. Now we know what's going on. So this is the main level set code. This is where I'm initializing, where I'm declaring the G function. I gave myself two residual vectors. I don't know if I'm going to be using them. I don't remember. And then this is my initialization. So at any point, so I loop over my domain, and I set G of ij, so like a phi of ij. At any point in our domain, I just set it to the value of this function called init Zalizak, which initializes the Zalizak disk. I give to it the position of my cell center, which is xm of ym of j. This little chunk of code was done in 3D, and so I didn't want to redo it. So I sent it to 0 third dimension. And then this is the location of the center of the disk. So the disk is going to be, the domain goes from, I think, minus a half to a half in both dimensions. So it's centered on 0. Above from the center, at a quarter of the domain above the middle, I'm going to center my disk. The disk is going to have a radius of 15% of my domain. It will have a notch width of 5% of the domain, and meaning a third of the radius, and a notch height of a quarter of the domain. And that's it. Okay? Any questions on the initialization? No, we're good. So moving away from this now, we have initialized everything. We're left with solving our equation. So I thought we're going to have to talk in quite a bit more details about this, or at least related topics tomorrow. So what we're going to do is spend just a bit more time talking about the flow solver, the equation solver that I have. So that's going to be part, whoops. So the last part here is going to be on the solution of our phi equation. Clearly, if you want to solve d phi dt is equal to sum minus a d phi dx in 1D, or alternatively minus d phi a dx. Well, this is a hyperbolic problem. And the hyperbolic problem requires some care. For stability. In particular, if we were to simply use central differencing, this would blow up. Okay? Because this is a simple hyperbolic problem like this with no diffusion is unconditionally unstable with an explicit time integrator and central differencing. So we have to use, we have to control our dispersive errors essentially, and to have controllable dispersive errors, we need to introduce for stability some upwind bias. So, for example, I'll say central differencing would blow up due to growing dispersion errors. So we need to introduce an upwind bias in our solution. That means that the flow direction will inform how we discretize our equations. And we need that for stability. So let's look at the local mesh quickly. We'll introduce a brief notation. So this is going to be my cell I. It's going to be I plus 1, I minus 1. We're going to stick to this form right here. The reason for this is just because it allowed me to copy and paste more from the already existing code. We're going to be running with divergence-free problems anyway, so this doesn't matter too much. So this is what we're going to be using. So that means that I'm going to have to estimate, and also I should mention that, well, let me state this directly. I will need to build convective fluxes at face I minus 1/2 and at cell I plus 1/2, here and here. Because we're using a staggered code for our velocity, this is already where we know our velocity, and since our velocity is going to be prescribed, we will have to do nothing about the velocity. So the only thing we'll really have to do is provide an appropriate value of phi, or in our code, an appropriate value of g at those faces. So that's going to be the challenge for us. Finding the flux values. So in our finite volume discretization, and you'll allow me to just assume first order forward Euler for the time integration. we're going to get that our phi at I at n plus 1 minus phi I at n over dt is equal to minus phi at I plus 1/2 at n times a at I plus 1/2 and at n minus phi at I minus 1/2 at n times a at I minus 1/2 at n, the entire thing over dx. So in this again, this is our velocity of the cell face. Same here, we know these, they're prescribed and they're already present at the cell face anyway, so we have nothing to do. Those two are the things we don't know. So we need to prescribe a discretization for them. So let's look at the guy on the left. Let's look at phi sub I minus 1/2. So let me, whoop, I keep doing the same thing. So the point again is we're going to use upwind bias to compute phi sub plus or minus, I plus or minus 1/2. So let's look at phi sub I minus 1/2. We're going to introduce a quick scheme for two reasons. First, it's going to give us third order accuracy. And some level of accuracy is required if you want to do interface capturing like this, or interface tracking, basically transporting interfaces. And it's going to allow us to upwind bias our solution. And the way it's going to look is the following. So now I'm interested in I minus 1/2. This is the value that I care about. Around it, I have as part of my solution process the value of my level set at cell I plus 1, at cell I minus 1, and at cell I minus 2. Okay? I need to go further out. I can't stick to the direct neighbors because I want to go for third order accurate. So there's really two ways. So if I want to get third order accuracy, I need to fit a second order polynomial, basically a parabola, through my data. Okay, then the next order error is going to be third order, or the leading order error will be third order. So that tells me I need to fit a parabola. To fit a parabola, I have to adjust three coefficients. To adjust three coefficients, I need to provide three stencil points. Okay, I have now 4 stencil points. That suggests that there's 2 possible stencils that I can use. I can introduce a green stencil, which would be using the 3 points on the left, or I could use the orange stencil, which would be using the 3 points or the set of rightmost 3 points. So we have 2 possible stencils. Well, now you can plug this, those points and your desire of fitting a paraboloid, or parabola in this case we're in 1D. You can fit that, you can write this out, do the Taylor series, build a Taylor table and generate the coefficients. What you find is the so-called quick coefficients. You find approximation 1, or I should say approximation orange really. Well, yeah, let me just, well, no, let's say 1. This is an approximation for this guy that will look like this. Minus 1/6 times phi I minus 1 plus 5/6 phi sub I plus 2 over 6 phi sub I plus 1. And that's using the 3 points, the 3 rightmost points. Anything wrong? Oh yeah, thank you. Good catch. And then the second stencil will be a phi I minus 1/2, which will be, well, it looks very similar. It's going to be 2 over 6 phi I minus 2 plus 5 over 6 phi I minus 1 minus 1 over 6 phi I plus 1. And that's going to be my green stencil. So we have 2 third-order discretizations available to us, and we're simply going to pick the one we use based on the local flow direction. It's going to boil down to this. If A sub I minus 1/2, so the A at our face, I wrote A here for this made-up little 1D problem, but it's really our velocity. So if our face normal velocity is positive, then we use, so the flow is going from left to right. We need to use the upwind bias stencil, so the one that uses more leftmost points. So that's going to be U stencil 2. If A sub I minus 1/2 is less than 0, we're going to use the stencil bias to the right, which is stencil 1. Okay, so we need something like that. We could do many other things. In particular, tomorrow we'll introduce something else. We'll introduce the concept of essentially non-oscillatory scheme, aka ENO schemes, and then we'll push that to the concept of weighted essentially non-oscillatory schemes, which are pretty much the de facto standard for solving the level set equations, because they are stable schemes that optimize in a very concrete sense the balance between dispersive errors that will be present and dominate and kill the solution if there's too much of them. It will balance dispersive errors with diffusive errors, which will allow you to run stably but degrade the quality of a solution. So the name of the game is, what is a discretization of a hyperbolic of those hyperbolic equations that allow you to minimize the diffusive errors while guaranteeing sufficient stability coming from the dispersive errors. This is really the name of the game. Okay, any questions on that? If not, well, let me switch to, so you should already have the code and have all this ready to go. Oh, well, no, I wanted to just show the corresponding little piece of code. This way you would have seen everything. So this is the corresponding code. I'm sticking to this Adam Bashforth approach, meaning that I really carry 2 residual arrays. I zero out my residual array number 1, and in number 2 I remember, well, first of all I remember the previous residual array in my array 2, and number 1 I zero out and then I calculate it, and then I combine linearly the 2 so that I have second order accuracy in time. Okay, so we have second order Adam Bashforth time integration of our equations, so I'm not doing forward Euler like in here, and I have this quick discretization. I'm looping over the entire domain, and at each point what I'm basically computing is the full residual, so I'm taking the divergence of my fluxes, which looks like this here. This is So there's 4 lines. The first 2 are the x fluxes. The second 2 are the y fluxes. The first 2, there's a minus and a plus. What they are is, the first one is for my face on the right. The second one is for my face on the left. Then this is my face at y plus above, and this is my face below. Okay, so I just go through each of my 4 faces. I could reduce the cost by increasing the storage, by computing the fluxes. Those fluxes are shared between cell faces, but it doesn't really matter. And then what I do is what I think mentioned already before. Instead of putting an if statement, I take the max of my local phase velocity and 0, and the min of that local phase velocity and 0. Okay, and then the upwinded part, I multiply by the max of the velocity and 0, because that will be equal to the velocity if this is if the velocity is more than 0. It will be 0 if the velocity is less than 0. And then the downwinded part, I multiply by the minimum between the velocity and 0, because it will be equal to the negative velocity if or to my velocity if the velocity is negative, or it will be 0 otherwise. So that gives me my on-the-fly treatment of my upwinding switch. And then this QM and QP, those are the plus and minus. Those are the 2 stencils that we derived a little bit before. And if you want to take a look at them, they're defined right here. They correspond exactly to what we wrote. One is minus 1/6, 5/6, and plus 2/6, and the other one is the same but read from the other direction. Okay? I think this is it. So let me unplug this. Any questions on what we're looking at the code here? No? Okay, so let me unplug this. So you should have 2 directories, one underscore zelizak, and then there's going to be a second one, and the one underscore zelizak, well, this is what we've just talked about. I don't think there's anything else we need to discuss about the source code. I told you it goes yeah, I think you know everything at this point. So you can run it. I set it up to run just for 1 rotation. So since and yeah, I think I mentioned that we just turned off the flow solver, so it goes ridiculously fast. So your domain should be a square-looking domain like this. I remove the perspective, I remove the highlighting. I'll create a cut through this at k is equal to 1. I think our mesh is 100 by 100. That looks like that's what it is. Let's take let's take first a oh, let me bring that back. So first of all, we can look at our initial condition. So this G field is what we talked about before. So this is not particularly exciting. Again, it's important to understand that this is essentially an elevation map as a function of space. So if you right-click on your sweep surface or your clip plane, you should be able to create this elevated surface. So as you go down this list here, one of the options should be an elevated surface, elevated by the variable g. If you create it and turn around, you should be able to see what this map looks like. I can remove the offset, and now you can see that part of this elevated map is underwater, the other part is above ground. So this is again really going back to this topographical perspective for this problem. Okay, that makes sense to everyone, the way this looks? Let me remove the elevated surface. It is not practical to look at this from the perspective of an elevated surface, but most scientific visualization tools have the built-in capability of generating an isosurface from a field. So we're going to do that here. We could do that manually. It's not a particularly complicated exercise to generate a collection of lines that represent a surface from a field. That would require interpolations and various levels of computer graphics. One tool in particular is called the marching cubes algorithm. The marching cubes algorithm is an algorithm that's been around for many decades that allow you to generate an isosurface from a field. So our isosurface is something we can create by clicking on the little, the three little droplets icon up here next to the scissors. If you click on this with your plane, your cut plane or sweep surface selected, you can create an isosurface. You have to provide a value. We're interested in the zero isosurface of this object. I'm going to make it thicker. I guess I'm not. Why is it not? Huh. I don't know why it's not changing thickness, but might be a bug in the new Insight. I'll make it black at least so that you can see maybe a bit better. So this is my isosurface. By the way, that isosurface, we could generate it at different levels, right? This is, right now, with our G field, or our phi field, we've generated a field in full 3D space. So I guess really in this case in full 2D space. That means that at any point we can generate an isosurface of that field passing through that point. But the only one to which we've assigned meaning in what we've done is the zero isosurface. But I have, I can traverse all my isosurfaces, and they're all going to be tracked along with the zero one. But again, because of our initial conditions, the only one that has meaning is the one at zero. But that also means that there's nothing that tells us that we should put our isosurface at zero. We could put it at a different value than zero if we wanted. That would be fine. So let me go back to a zero value here. That doesn't look like a zero value. What did I do? There you go. So this is our isosurface. Is everyone on the same page here? We're all looking at the same thing? I'll change my color scheme by editing the palette that you can find in the Surface Property Editor to make it symmetric about zero. And I will also make it plotted continuous so that it looks nicer. So this is the smooth auxiliary function that we're going to be tracking in this. Now I'm going to add to this the velocity field because, yes. So what did I do? Do you have the isosurface? So to get the isosurface, you click on your clip plane or sweep surface, whatever you created, and you go to this icon here, the three little drops, okay? And then you select as a variable the G variable, and you're going to set a value for isosurface of 0, and then down there you create. Yes, that's fine because you're looking at the final time. I'm still in my initial
Okay.
I'm on my initial time, so the initial time should look sharp.
Oh.
There you go. So you're looking at the numerical errors, which is fine. Okay, so that looks fine. I was at the initial time. That looks fine. Your isosurface here is plotted at a large negative value. If you just plot it at 0, and this is now what you want. Yeah, looks great. The reason why it looks different from what I have is because you had the final simulation time. Okay. You're trying to set up the clip plane? Okay, so if you click on Tool here, go to IJK. Okay, now you're going to select K and create. Okay, you can close this. Now you're going to color this plane by the G variable. Okay, you can close. So far I was looking at the initial condition, so you can bring this cursor all the way back to 0 from here to here. Okay, so this is our initial condition, and now we can go here and create from this thing here using the G variable and putting here a value at 0. You can now create an isosurface. There you go. Okay? So everyone is, I think what you did is you created your isosurface from the elevated surface. So let me delete this and delete this. And now you go here and you redo from here the isosurface of G, and that should look fine. All good. Excuse me.
Level set field.
So you have this guy is colored. The surrounding surface has been colored. So let's leave it a constant color. I don't know how this one was created. So let's redo it. We're going to select this guy, create a cut at IJK, but we're going to cut in K, so that we cut really in the Z direction. Now we end up with this plane, and now you color by G. I was showing here the initial conditions, so we go back to initial time, and then here you go and you create, you see the little droplets here, you create an isosurface of G at 0, and there you go. All good?
What range do you use over there?
Yeah, I think that's what I use. Yeah. Okay, so the reason why it looks smooth on my screen and not on yours is because let me show you up here. The data we're outputting it tied to the cell, not to the point. So by default, nSight will assign a value to the cell, not to the point. You can tell it to override that by going to your sweep surface or your cut plane, whatever you call that. Click on the coloring, go to Edit Palette, and that's the various coloring options. You're going to go, there's multiple tabs below the place where you set the range. Click on the Option tab, and the type of coloring is what you need to change. If you're constant, you have the true visualization where each cell is colored by the value that you've assigned to that cell. So it makes everything look not quite as nice because you have one value per cell, period. If instead you want to make it, you want to visualize your field by a smoothly interpolated visualization, then you say continuous, and everything will look smooth. So the one thing I wanted to show was the velocity field. So let me create one more thing that I think we haven't done so far. We're going to go to the right of our pair of scissors here, and we're going to select the vectors, and we're going to show arrows for our vector field. We'll leave everything we'll use the default values for everything here, and we'll create. So that is your solid body rotation velocity. If I zoom out, it becomes really overloaded with vectors, very tiny little vectors. So I'll make those vectors larger, but I'll put only 10% of them. So I've reduced the density to 0.1, but I've made them significantly larger. Yeah, somehow I cannot change the thickness of those objects, but it doesn't matter. Okay, so you can see the solid body rotation velocity field very clearly here. This is a purely linear velocity field spinning around the center of our domain. This thing should just go around and arrive right here. So we stored 10 time stamps over the course of the rotation. I'm at time 0 here. As I integrate this forward, you can see that we get the right, or the expected behavior. So by transporting this function g, using this simple advection equation, we've been able to transport along with it this black isosurface that we added on this image. This is the entire point of the level set method. We didn't do anything to explicitly track our surface. What we did is we introduced an auxiliary field, and then the forward transport of that field in time allows us now to know an estimate of our distance from the interface at all points.